projects. In this video, we are going to explain about the project title Lung GANs Unsupervised Representation Learning for Lung Disease Classification using chest CT and X-ray images. Introduction. The project primarily aims to address the diagnosis of critical lung diseases, including COVID-19, given the substantial impact on global health. These diseases often lead to significant morbidity and mortality rates worldwide, highlighting the urgency for improved diagnostic methods. Traditional diagnostic methods heavily rely on chest X-ray and CT scans. However, these methods pose challenges in interpretation, which result in delays in diagnosis. Moreover, the accurate interpretation of these scans requires a high level of expertise from radiologists, contributing to potential errors and longer diagnosis times. The project introduces Lung GANs, an innovative deep unsupervised learning system utilizing generative adversarial networks (GANs). This system is designed to autonomously learn and extract intricate patterns and features indicative of lung diseases from raw, unlabeled data. The primary goal is to expedite diagnosis while maintaining accuracy by leveraging advanced machine learning techniques. Leveraging advanced deep learning methodologies such as GANs signifies a paradigm shift in lung disease diagnosis. The project's objective is to offer a faster, more reliable, and potentially more accessible diagnostic tool for healthcare professionals. By integrating these cutting-edge technologies, the project aims to significantly improve the efficiency and accuracy of lung disease diagnosis, ultimately benefiting patients and healthcare systems alike. Objective: GANs are a type of neural network architecture consisting of two parts, a generator and a discriminator. These networks work in tandem to generate synthetic data resembling real lung images or aid in extracting features relevant for classifying lung diseases. The project involves using TensorLayer, a deep learning and reinforcement learning library, to train and test the GAN architecture. The Adam optimizer, an optimization algorithm, is utilized to update network weights during training. Specific hyperparameters such as learning rate and batch size are adjusted to ensure the GAN performance optimally. Additionally, the project includes creating an ensemble of classifiers employing methods like random forest and linear support vector classification. These classifiers are trained individually to classify lung disease instances. The goal is to evaluate how combining predictions from diverse classifiers can potentially enhance overall accuracy. The objective is to develop diverse classifiers that exhibit strengths in different areas of lung disease classification. By ensuring that each classifier makes errors at distinct instances, when the predictions are combined, the expectation is that these errors will offset each other, resulting in an overall more accurate classification. Software and hardware requirements. Software requirements of the project are: software is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have utilized the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages in the chosen programming language. Commonly used libraries include NumPy for numerical computations and array operations, Pandas for data manipulation and analysis, Matplotlib or Seaborn for data visualization, TensorFlow or PyTorch for building and training deep learning models, and Torch Vision, a part of PyTorch that offers tools for computer vision tasks. These packages provide essential functionalities required throughout the project. Exploring the dataset, COVID-19 data. This phase focuses on understanding the dataset related to COVID-19, which contains chest CT scans or X-ray images. Steps involved: loading the dataset, reading the data into the programming environment, data inspection, checking the structure, size, and format of the dataset, data visualization, creating visualizations to understand distributions, patterns, and characteristics of the data, Understanding the dataset aids in formulating strategies for pre-processing and model building. Image processing using image data generator. Rescaling the image. Adjusting pixel values to standardized range, usually between 0 and 1. Shear transformation. Distorting the shape of images by shifting one part of the image. Zooming the image. Altering the size of images. Horizontal flip. Flipping images horizontally to create mirror images. Reshaping the image. Adjusting the dimensions of images to fit the model's input requirements. Torch vision based processing for detection. Utilizing torch vision functionalities for specific image processing tasks. For instance, detecting objects, extracting features, or applying filters in the context of lung disease diagnosis. Building the model. Constructing a generative adversarial network GAN architecture comprising a generator and a discriminator. Training the GAN on the chest CT and X-ray images to learn representations of features related to lung diseases without explicit supervision. These images serve as the primary dataset for training and optimizing the GAN model. The GAN aims to capture crucial features and representations that aid in the accurate classification of lung diseases. Training the model. After constructing the GAN architecture, this phase involves training the model using the prepared dataset of chest CT and X-ray images. The training process involves feeding the images into the GAN and optimizing its parameters iteratively to learn representations of features related to lung diseases. The objective is to achieve a well-trained GAN that can effectively capture essential information for accurate lung disease classification. Flash framework with SQLite for sign-up and sign-in. Utilizing the Flash framework, which is a web framework in Python, to create a web application. Integrating SQLite, a lightweight relational database for user authentication functionalities such as sign-up, user registration, and sign-in login. This allows users to create accounts, log in securely, and access the lung disease analysis functionality. User upload an image for analysis. Users interact with the web application to upload their chest CT or X-ray images for analysis. This step involves the user interface, allowing users to select and upload the images to the application. The given input is pre-processed. The uploaded image undergoes pre-processing steps to ensure it's in a suitable format for model prediction. This involves resizing the image to fit the model's input size, normalization, or any required transformation to align the image with the format expected by the trained model. The trained model is used for predicting the result. The pre-processed image is passed through the trained GAN-based model. The model uses the learned representations of features to predict the presence or classification of lung diseases in the uploaded image. Final outcome is displayed through front end. Once the model makes prediction, the results are displayed to the user through the front end of the web application. The user interface shows the analysis outcome, which includes information about the predicted lung disease or relevant diagnostic details. Algorithms used to implement this project, we have utilized the following algorithms. The first one is GAN, that is Generative Adversarial Network. GANs consist of two neural networks, a generator and a discriminator engaged in competitive game. The generator creates realistic data, that is lung images, while the discriminator tries to differentiate between real and generated data. Through this competition, the generator learns to create increasingly realistic images. GANs are used for unsupervised representation learning. They can learn representations of features from the chest CT and X-ray images without requiring explicit labels or annotations. In this project, GANs are employed to generate meaningful representations of lung diseases, aiding in classification tasks. Linear SVC. Linear support vector classification is a linear classification model that operates by finding the best hyperplane to separate classes in a high-dimensional space. It aims to find the optimal linear boundary between different classes. Linear SVC is utilized as one of the classifier in the ensemble learning approach. It provides a simple yet effective classification method, contributing to the diversity of classifiers used in the project. Random forest. Random forest is an ensemble learning method based on decision tree. It constructs multiple decision trees during training and outputs the class, that is, the mode of the classes or mean prediction of the individual trees. Similar to linear SVC, random forest is employed as another classifier in the ensemble. Its strength lies in its ability to handle high dimensional data, capture complex relationships, and reduce overfitting, contributing to a diverse set of classifiers for improved accuracy. Voting classifier. A voting classifier combines multiple individual classifiers and aggregates their predictions to generate a final prediction. The voting classifier is used to combine the predictions made by different classifiers such as linear SPC, random forest, and possibly others in the ensemble. By combining the outputs of diverse classifiers, the voting classifier aims to improve overall accuracy and robustness in lung disease classification. As an extension, we applied an ensemble method that combines the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how our model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the comparison graphs of CT datasets. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm, which is performing best in all the performance metric, will be used for prediction. Comparison graph of X-ray dataset. This is the accuracy comparison graph. This is the precision comparison graph. This is the recall comparison graph, and this is the FN comparison graph. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb file. These are Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.tb file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I have copied the path. Now open the Anaconda prompt. use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register, but I have already registered. So click here. So here we need to enter the username and the password which we have registered, and then click on login. We have logged in successfully. So here we can see a classification link. In this project, we have utilized two data sets, that is CT and X-ray. We will execute the project using the first data set, that is the CT. So first click on it. So here we need to upload the image to predict whether the patient is having COVID-19 or not. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is diagnosed with COVID. Now let us upload some more images and check the result. Click on CT. Now click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is not diagnosed with COVID. In this way, by uploading the image, we can classify whether the patient is suffering with COVID or not. Now click on classification link. Now we will execute the project using another data set, which is X-ray. So click on X-ray. So here we need to choose a file. Click on choose file. Select the image. Click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is diagnosed with COVID. Now let us upload one more image. Click on classification, click on X-ray. Now click on choose file. Select the image. Click on upload button. This is the uploaded image and it is predicted as the patient is not diagnosed with COVID. In this way, we can predict whether the patient is suffering with COVID or not using the two different data sets. Now we will do detection. So click on detection link. Now click on CT to do the detection using the CT data set. Click on choose file. Select the image. Click on open. Now click on upload button. This is the uploaded image and here we can see that we have detected that this person is suffering with COVID and it is written on top, and here we can see the probability score. Now let us upload some more images. Click on detection, click on CT. Click on choose file. Select the image. This is the uploaded image, and here we can see that it is detected, and on top it is written non-COVID. It means the person is not suffering with the COVID. And here we can see the probability score. Now we will do the detection using another data set, which is X-ray. So click on X-ray. Now click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image, and here we can see that the person is suffering with COVID and it is detected by a red color bounding box. And here on top we can see the probability score as well. Now let us upload one more image. Select the image. This is the uploaded image, and here we can see that the person is not suffering from COVID, and it is written on top that is non-COVID, and this is the probability score. And here we can see the detection. In this way, by uploading the image, we can detect whether the person is suffering with COVID or not. Now click on sign out. The conclusion of the project is: the conclusion highlights the effectiveness of using unsupervised representation learning, specifically generative adversarial networks (GANs), to diagnose lung diseases using CT and X-ray images. GANs demonstrate their capability to extract meaningful features without heavy reliance on labeled data, showcasing their efficacy in medical image analysis. It emphasizes the project's achievement in significantly improving diagnostic accuracy without requiring extensive labeled data. This advancement marks a departure from traditional methods that often rely on large labeled datasets, showcasing the potential of unsupervised learning techniques in medical image analysis, where labeled data might be scarce or costly. The project contributes to streamlining the diagnostic process for lung diseases. This framework simplifies the diagnosis, benefiting both experienced radiologists and less seasoned physicians. By facilitating more precise and timely diagnosis, it has the potential to enhance patient care by enabling quicker and accurate decision making. The conclusion suggests future directions for improvement, highlighting potential areas of research and development. It indicates the need for refining existing models, exploring newer neural network architectures, or integrating advanced technologies. This emphasizes the continual nature of research efforts aiming to further refine and enhance diagnostic capabilities in the field of lung disease diagnosis from medical images.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.